Okay, get ready for a wild ride because today we're diving headfirst into the world of particle physics.
That's right. We're talking about a paper that has physicists, well, kind of freaking out. And let me tell
They
you,
don't get excited easily.
not at all.
Hmm.
What's got them buzzing is the potential of this research to uncover new physics.
Do physics. Okay, now that does sound exciting, but
And no, I'm not talking about warp drives and spaceships here.
okay, good to know. So what are we talking about? Like, are we going to have to rewrite the physics textbooks?
Well, in a way, yeah. You see, we've got this thing called the standard model, right?
Yeah.
It's like our current best understanding of how the universe works at the tiniest level. And it's
Yeah.
been crazy successful, explaining a ton of stuff. But here's the thing. It's got some holes, like big ones. It can't explain things like dark matter.
Oh, right, dark matter. Everyone's always talking about that.
Right. Or even why gravity is so weak compared to the other fundamental forces.
Yeah, gravity's kind of the weird one out when you think about it.
Totally. And that's why physicists are so hyped about this paper. It's like we found this whole unexplored wing in the library of the universe.
Oh, I like that. An unexplored wing full of secrets.
Exactly. And you know what? This paper, it's about using this brand new tool to explore that wing. A tool powered by, get this, artificial intelligence.
AI and particle physics. Okay, now that is a combo I did not see coming. So how does that even work?
Picture this. The Large Hadron Collider, the LHC, this giant, super powerful particle accelerator,
Okay, yeah, I've heard of that. Smashing atoms or something, right?
smashing particles, even smaller than atoms, at insane speeds. It's creating this like cosmic symphony of data.
Wow.
But, and there's always a but, that data, it's insanely complex and messy, like trying to find a specific grain of sand on a beach.
Okay, yeah, that does sound like a job for, well, something a lot smarter than us.
Chuckles. Right. And that's where graph networks enter the picture. They're this type of AI that's really, really good at finding patterns and connections, even in the most chaotic data sets.
Ah, okay.
So this paper is proposing that we use these graph networks to sift through all that LHC data,
Makes sense.
looking for the tiniest hints of these new particles and forces that we haven't discovered yet.
So it's like giving, like, Sherlock Holmes a superpowered magnifying glass.
Exactly.
He can see clues that were invisible before.
Precisely.
Mm.
But even with this superpowered AI, there are still some big challenges. That's actually why this paper is causing such a stir. They've tackled two of the biggest hurdles that have been holding back this type of AI in physics research.
Okay, now I'm really intrigued. What are these hurdles, and how did they get over them?
Okay, so hurdle number one, it's all about making sure this AI actually plays by the rules of physics.
Okay.
We're talking about something called infrared and collinear safety. It's kind of like a safety net, making sure the AI doesn't make, well, embarrassing mistakes.
Embarrassing mistakes, like what? Give me an example.
Okay, imagine you're looking at a blurry photo, right? And you keep zooming in, thinking you'll magically see more detail.
Right, we've all done that.
But in reality, you're just getting a bigger blur. You can't create information that wasn't there to begin with. And it turns out, in particle physics, there are these similar limits to how closely we can actually look at a particle collision before our calculations just sort of, I don't know, start making sense.
Huh, so it's like there's a fundamental fuzziness to the universe at that scale.
You got it. And that's what this infrared and collinear safety is all about. It's like teaching the AI to understand those limits, making sure it doesn't zoom in too far and start seeing things that aren't really there.
Okay, so it's like teaching the AI the boundaries of reality, in a way.
Exactly. And the way they built this directly into the AI is honestly genius. It's like giving it this intuitive sense of what's physically possible and what's just, nonsense.
That's amazing. Okay, so hurdle number one, making sure the AI doesn't go bonkers. What's the second challenge?
Challenge number two is all about making the AI more, how to put this, physics aware. Basically giving it this deeper understanding of the symmetries and patterns that we know are fundamental to how the universe works. We call this equivariance.
Equivariance. Okay, yeah, that one's going to take a few more times to roll off the tongue. Can you give me an example of what you mean by symmetries in physics?
Sure. Okay, imagine a square. You can rotate it, flip it, but it still looks like a square, right?
Yeah, its basic shape doesn't change.
That's symmetry. And in physics, we see these kinds of symmetries everywhere. The laws of physics don't just randomly change depending on, which way you're facing.
Right. That would be chaotic.
Total chaos.
Yeah.
And for the AI to really understand these particle collisions, to make sense of that mess of data, it needs to understand these symmetries too. It needs to get that the laws of physics are kind of universal, no matter how you look at things.
So we're basically teaching this AI to see the universe, not just with, like, super sensitive instruments, but with a physicist's eyes.
That's a great way to put it.
That's really cool.
Yeah.
Okay, so it's got this equivariance, this symmetry sense, but does it actually help it find those new particles, like, faster?
Oh, absolutely. Think of it this way. Because the AI now understands these symmetries, it can basically ignore a ton of irrelevant data.
Oh, okay.
It's like, imagine you're looking for a specific quote in a book, right? You don't have to read every single page.
You can just use the index.
Exactly. You use the index. And that makes the whole thing way faster, way more efficient. That's what this symmetry awareness does for the AI. It helps it zero in on those new physics needles in the haystack of LHC data.
That's so cool. Okay, so we've got our AI all decked out, right? It's got its safety net, it's got its symmetry sensing superpowers. What kind of physics mysteries are we sending it to solve?
Well, in this paper, they decided to test their AI on this really tricky problem, something we call semi-visible jets.
Semi-visible jets. Okay, now that just sounds made up. What is that?
I know, right? It does sound kind of sci-fi. But trust me, these jets, they're just as cool as they sound and just as hard to find. Imagine trying to track a stealth bomber on radar.
Oh, okay, so they're kind of like the ninjas of the particle world, but not visible.
Exactly. See, these semi-visible jets, they involve particles that our detectors, they can't see directly. They just interact so weakly with normal matter that they pass right through our detectors like ghosts.
Wow, okay, so how do we even know they're there if we can't see them? It's like trying to study a shadow without having the object that's casting it.
Now you're getting it. That's a great analogy. We have to look for the subtle effects they have on other particles, the whispers and echoes they leave behind in the data.
Okay, I think I get it.
And that's where this super sleuth AI comes in.
It can pick out these faint signals that our instruments would just miss completely.
You got it.
That's wild. But what are we hoping to find with these semi-visible jets? Like, what's the big deal?
Well, they could be the key to some of the biggest mysteries in physics. For example, there's this idea called hidden valley models.
Hidden valley models. Okay, now we're definitely in sci-fi territory.
I know, right? But it's such a cool idea. It suggests that there might be these whole hidden sectors of particles out there.
Wait, like parallel universes?
Not quite parallel universes, but it's kind of similar in a way. These hidden sectors, think of them like secluded valleys, right?
Yeah.
Separated from our familiar world by these huge mountains of high-energy physics.
Okay, I'm following you.
And we might not be able to climb those mountains directly, but these semi-visible jets, they could be like messengers from those hidden valleys.
Wow, that's mind-blowing. Okay, so did the AI, did it actually find them? Was it able to track down these stealthy semi-visible jets?
It did, and the results were incredible.
Yeah.
It just crushed the previous methods, especially when it came to analyzing data sets that were really limited.
So it's efficient, too.
Super efficient. It's like our AI detective solved this case with just a couple of fingerprints and a blurry security camera image.
Wow, that's amazing.
And the implications of that are huge because it means we might be able to make these groundbreaking discoveries even with the data we already have.
That's so cool. It really seems like this research, it's not just about finding one new particle or proving one theory. It's like giving us this whole new way of looking at the universe.
You got it. Exactly. The potential for this kind of AI-powered physics is just, it's mind-boggling. It's like we've been using a magnifying glass to study the cosmos this whole time, and now we finally have our hands on a high-powered telescope.
That's a great way to put it. And I can't wait to see what we discover with it.
Me neither.
But before we get too carried away, let's bring it back down to Earth for a second. What does this mean for us? For the average person who doesn't spend their day smashing particles together?
That's a great question.
Yeah.
And it's important, right? Because this isn't just about abstract physics equations. It's about pushing the boundaries of what we know, of what's possible.
Totally.
And who knows what amazing technologies, what innovations might come out of that, a deeper understanding of the universe.
Right, because when we understand the fundamental rules, we can...
You can do amazing things.
Yeah.
I mean, who knows, maybe this research will lead to clean energy solutions or
maybe even faster than light travel.
hey, you never know.
Yeah, exactly. It's not just about satisfying our curiosity. It's about pushing the limits of knowledge.
Exactly.
And who knows what could come from that.
And you know what's even more mind-blowing? Imagine if we can train AI to find things we already had a hunch about.
Right.
What about the things we have no idea about?
Yeah.
What completely unexpected discoveries might be hiding in that data, just waiting for the right tool?
That is what is so exciting to me about this whole thing.
Yeah.
It's like we're giving the AI a treasure map, but we don't even know what's on it.
Exactly.
We have no clue what riches it's going to find.
Exactly. Yeah. And it could be anything.
We're talking about potentially rewriting textbooks here.
Absolutely. I mean, we could find completely new particles,
Yeah.
new forces, maybe even evidence for extra dimensions. Who knows?
It's wild.
It's crazy.
It's like we could fundamentally change how we understand the universe.
Yeah, I mean, this AI, it could be our guide to a whole new understanding of, like, everything.
It's incredible to think that, we're alive at a time when this is even possible.
I know, it's amazing.
It's really a new era of science.
Yeah, this fusion of human ingenuity and AI.
Yeah.
It's incredible.
It's very cool. And this is only the beginning, right?
This is just the start. Yeah, exactly.
Like, as we keep developing these techniques, who knows what else is out there?
Who knows what's next? That's the exciting part.
Exactly. Well, I am very excited to find out.
Me too.
I have a feeling our listeners are too.
Yeah, I'm sure.
So for anyone who wants to dive into the nitty-gritty details,
all the details.
We'll have a link to the full paper in the show notes.
Definitely worth a read.
It's a fascinating paper.
It is.
So until next time, stay curious, everyone.
See you next time.
And keep exploring. From the frontiers of AI and particle physics, this has been The Deep Dive.